Good morning or afternoon, depending on where you're Zooming from. My name is Erin Kirby, and I'm the Senior Director of Advancement for the University of Illinois Research Institutes. I'm Zooming from my home in Champaign, Urbana today, so welcome. We're glad you've joined us for this Zoom presentation entitled COVID-19, Climate Change and Health. This talk will feature three prominent University of Illinois faculty discussing lessons we can learn from the interplays between climate and human health in the wake of the COVID-19 shutdown. The panelists will answer questions at the end of their talk, so please submit your questions in the Q&A area at the bottom of your screen. You can also rank other questions that have already been submitted. If you like those rather than typing in a new one, we'll be monitoring that throughout the talk, and we'll address them at the end. You can also, we're also recording today's presentation, so we'll send that out to you later this week, and you're free to share that with others. Our first speaker today is Professor Don Wuebbles. Dr. Wuebbles is the Harry E. Preble Professor of Atmospheric Sciences in the Department of Atmospheric Sciences within the School of Earth, Society, and Environment. Dr. Wuebbles is a University of Illinois Presidential Fellow and was one of the first faculty at Illinois to be named a Blue Waters Professor. He provides frequent analysis and development of metrics used in national and international policy. And from 2015 to 2017, he was Assistant Director with the Office of Science and Technology Policy at the Executive Office of the President. He was where he was the White House expert on climate science. Dr. Wuebbles will begin our presentation now, and we'll talk about climate change, the underlying science, and how the quarantining around the world has affected emissions causing climate change. Take it away, Don.
Thank you. Well, thanks everyone for being on this. I want to thank all my fellow alumni. I have 2 degrees from the University of Illinois. I got my bachelor's and master's degree at Illinois. And then never expected to come back, but did so 25 years ago to be department head of the Department of Atmospheric Sciences. And I've done a lot of other things since. What I'm going to do today is along with my colleagues, Dr. Ashish Sharma and Professor Larry Girolamo, is to talk about COVID-19, climate change, and health. I'm particularly going to come at it from the climate change perspective and start out with a description of how our climate is changing, and then what's happening recently relative to the quarantine. And so I'm going to start going through the slides. First of all, it's kind of important to understand the difference between weather and climate. So weather is what we see every day. It's it's what you expect at a given, or what you find occurring at a given time, such as today being kind of cloudy and semi-rainy here in central Illinois. And whereas climate is the long-term averages and statistics of weather. And so we tend to talk about 20 or 30-year time periods. Another way of looking at this is the way Mark Twain is attributed to have put it, which is that climate is what you expect, and weather is what you actually get. So, so the weather may be typical or untypical of what's going on with the climate. And as you all know, our climate is also changing. So why care about climate and climate change? One way of thinking about that is climate affects everything around you. The landscape, the severity of the weather in your particular part of the country or wherever you're at in the world, the availability of what kind of food tends to be there, water availability, what all the different animals and plants that you tend to see in your area, and also associated health risk. Why this might matter, why climate change might matter is, suppose a summer in Illinois by the end of the century might look more like that in eastern Texas, where we having potentially most of the summer being 90 degrees Fahrenheit or above. That's not Illinois as the climate we know now. And so yet this is the kind of climate we might see if we continue to follow the high emissions case that I'll be talking about. So Every year, there's about 12,000 different papers published about climate and climate change. And so it's not surprising that different world bodies have decided that we really need to understand what that means to the people around the world, and in our case, especially the people in the United States. So that led to the formation of the IPCC, the Intergovernmental Panel on Climate Change, a UN body that brings together scientists every 5 or 6 years and tries to look at climate change. The picture on the left is the cover from the 2013 assessment, the last assessment called Assessment Report 5, AR5, and there's a new assessment going on right now. I actually led chapter 1 of that of that assessment. Then the other two pictures deal with the fourth National Climate Assessment. I co-led volume 1 relating to the science of climate change. And that was published in 2017, in November 2017. And then the second volume, which I also co-authored, was relating to the impacts on the American people from climate change. And that was published in November of 2018. So what do these kind of analyses tell us? Well, our climate is changing. It's changing now. It's well observed that we're seeing rapid changes occurring. In fact, these changes are so rapid that they're about 10 times more rapid than changes have tended to occur naturally since the end of the last ice age, at least. And shows that the kind of changes we're seeing are very difficult for human society and for ecosystems to be able to deal with because of these very, very rapid changes. It's not just all about temperature change. It's not just global warming, which is why scientists have always tended to call it climate change. Biggest concerns are probably the changes in severe weather that are becoming more intense. Talk a little bit about that in the next few minutes. And at sea levels are rising and oceans are being affected. We won't deal too much with that today, but we'll touch on it. And why is all this happening? Well, it's largely happening because of human activities and associated pollution. And I'll talk a little bit about that. The drivers largely being connected to our use of fossil fuels and also to land use change. One of the things we know is that the climate will continue to change over the coming decades, but how much it changes really depends on us and our choices. And we'll talk a little bit about that as we go through this. So first of all, I want to make it very clear that these assessments and the data we use is largely based on observations. So it's not just of temperature, it's a number of other aspects, what's going on in the oceans, what's going on with the ice, what's going on in the atmosphere in terms of humidity. A warmer atmosphere should hold more water vapor, and that's exactly what we see, that the amount of humidity in the atmosphere is increasing. Because of the increasing temperatures, the amount of land ice and ice in the oceans are generally decreasing. So, so this is just some examples of the very data-driven aspects of these assessments. Now, one thing you should be aware of is actually a former Illini, a graduate of Illinois, Charles David Keeling, went by Dave Keeling, is the way I used to know him. Began very, very accurate measurements in 1957 in Mauna Loa, Hawaii, then showed very rapidly that the amount of carbon dioxide in the atmosphere was increasing. And so you can see the annual cycle in carbon dioxide here due to plants breathing and the biosphere around us essentially using CO2 during the summer and it going back in the atmosphere in the winter. But on top of that is this very significant increase in carbon dioxide we've seen since, such that overall, we've seen about a 40+% increase in the amount of carbon dioxide going from pre-industrial levels of about 300 parts per million now to over 410 parts per million. What this graph shows you here is that the amount of carbon dioxide has changed dramatically over the last 800,000 years from ice core analyses, where they trap the bubbles trap the carbon dioxide inside of bubbles that are caught inside the ice, And so you can see that during the ice ages themselves, the amount of carbon dioxide was tending to be smaller, more like 200 parts per million concentration. In between ice ages, it tends to be 280 to 300, and now we're over 410. So this is very unusual. In fact, it's likely that we have not seen such carbon dioxide levels for the last 3 million plus years. And the last time that those levels were so high was a much, much warmer Earth than now. Maybe giving us some lessons about what's to come yet. What is driving climate change? Many lines of evidence demonstrate that human activities, especially emissions of greenhouse gases, that's carbon dioxide and methane and some of the other gases that can trap infrared radiation in the atmosphere and help provide a blanket of warming to the Earth, but unfortunately we're increasing the amount of that blanket. And these gases are primarily responsible for the observed climate change. The graphs on the right just show that we cannot explain the observed temperature record over the last century without accounting for the human activities. For the periodic storm of the last century, there are no credible alternative explanations. It's not the sun. We know that the sun has actually decreased slightly in terms of its output, not increased over the last 50 years. It's not natural cycles. There are no natural cycles that we can explain. You see these things in the media all the time, but that's not what's going on. Well, now I want to look at what's going on with energy now. What's happening to these greenhouse gases now? So if we look at the coronavirus event and the fact that everyone around the world has been largely staying in their homes over the last several months or before that there has been a significant decrease in energy demand as a result. So there's been a sharp drop in energy, and we haven't seen such a rapid change in quite a number of decades, probably at least back to World War II and perhaps the last pandemic and major pandemic in the 1918 to 1920 time period. But here we are. So we've seen about a 5 or 6% decrease in overall demand. If we look at some of the specific aspects, different countries and around the world, there's been a much less road activity. So transportation is decreasing, number of flights has decreased dramatically. If we look at the overall electricity demand, the demand is down in most countries of the world because of people staying home. And so we've seen on the order of a 5% decrease worldwide. This is the largest decline since the Great Depression. Impacts have been largest in Europe and the United States, but do extend over all corners of the world. Now, if we look at the projections for what's likely to happen over this, the rest of this year, it's generally assumed that we will start to recover over the coming months. That the demand will start picking up again as people go back to work and around the world and businesses come back into play. The question is this being a little over optimistic? Are we going to have so many more impacts because of people doing that the pandemic gets worse for a while? That's unclear. But if we use these analysis that came from the International Energy Analysis that came out recently, then we would assume that on the order of about a 6% total reduction in emissions over this, or 6% reduction, sorry, in fuel demand over this year. And in particular, one of the things to note, though, is renewables is actually increasing as the amount of solar and wind and other renewables is tending to increase worldwide. This year, there'll probably be an overall increase in those because that's where the energy will go first, because once they're installed, they're almost free. But we're likely going to see a significant reduction in coal, gas, and oil during this year. Now, if we look at the what's happened this year versus any particular year in terms of CO2 emissions, the carbon dioxide emissions that result from the burning of fossil fuels, this is likely to be the largest single year of a drop in those emissions. But whether it's going to be 6-8% or so is not clear yet. If we look at the actual data, we see that this is the time of year when the carbon dioxide levels are changing very dramatically, as plants are coming into in the northern hemisphere are really increasing their production, drawing CO2 out of the atmosphere, and that is making for a pretty sharp change in the amount of carbon dioxide in what's measured. And you can see that in the red graph, which shows pretty recent measurements actually through the end of last month. And so we just can't really tell yet what kind of effect there's going to be on CO2, but the effect may be overall less than some of these projections have suggested. Or it could be the 8 to 10% for this year. But if we look at the future, the question is what's going to continue to happen. So let me just give you some concluding thoughts. Climate change is happening now, and the impacts are projected to increase. Many different types of impacts are likely to be of concern. Warmer summers, new temperature extremes, precipitation coming as larger events, more flooding, which I didn't get really much time to talk about. Those are things that are particularly happening here in the Midwest, but really affecting people throughout the world. In general, the dry are getting drier and the wet are getting wetter. So the dry parts of the country or parts of the world are likely to get drier. And here in the Midwest and the Northeast, we're likely to see wetter conditions. And rising seas are continuing to be an issue affecting many coastal areas around the world, including particularly the East Coast of the United States is likely to be greatly affected. And you couple these with storm surges from large storms, particularly hurricanes, that can end up being really major issues over the next few decades. COVID-19 will slow down all this down, but likely only slightly, really depending on what happens over this next year or so, unless the lessons learned from COVID-19 were to provide warning to our society to really take climate change seriously, that we need to be doing something about this, in which case maybe we could make these a long-term reduction in emissions. And I will leave it there and turn it over to Ashish. Ashish is the Illinois research climatologist at the Illinois State Water Survey, and is also an adjunct assistant professor in my department, the Department of Atmospheric Sciences, and affiliate also with the National Center for Supercomputing Applications. He's going to present satellite data, talk to you about air quality in various parts of the world, and then what that means to health as well. And so it's all yours, Ashish.
Thank you, Don, for the introduction. Welcome everyone. I will primarily be showing the impacts of COVID-19 on air quality, as Don mentioned, and what can we learn from it. Some of the figures that you will see on the slides are taken from public data sources, and many of them are the results of our collaborative work within the University of Illinois and colleagues at NASA and other universities and institutions. Okay. So let's start from China, because this is all where it started. So if we look at COVID-19 and air quality impacts in China, COVID-19 originated around late December of 2019 in the city of Wuhan in China. And COVID-19 is a scientific name for coronavirus told by World Health Organization. And here, what I'm showing is the NASA OMI tropospheric cloud screened NO2, that's nitrogen dioxide. And you can see its evolution from 1st December to late March. And this in the circle, you see Wuhan, and you can see eventually the NO2, which is a proxy that we're using for air pollution, because NO2 is normally emitted from anthropogenic sources and industrial sources. So as the activity reduces, we believe the NO2 also reduces in the atmosphere. So to contain the outbreak, China began its lockdown or shutdowns on January 23 in Wuhan and eventually throughout the country. If you look at this map that I'm showing, the visualization, it doesn't clearly show what's the impact of NO2, because NO2 has a lot of daily and seasonal variability. So what we did is we looked at the changes in observed tropospheric NO2 through satellite data, and we are comparing the year 2020 in comparison to a decadal mean from 2010 to 2019. So we are taking a period of January 23 to March 16, almost 1.5 to 2 months. And here you can see the visualization, which shows the differences, the swipe map of tropospheric NO2 concentration. So clearly you can see the air quality is improved. But the coronavirus, that's the focus today, it didn't just stay in China. It spread because of its high transmission. And on March 11, 2020, World Health Organization declared COVID-19 a pandemic. By a pandemic, we mean a global disease. So as it progressed, it reached Europe by mid-March, and Europe banned its travel, and a lot of countries within the Europe started locking down or shutting down their countries or cities. And here again, I show the similar visualization of NO2 for March 2020 compared to a decadal mean that is for March from 2010 to 2019. And you can see reductions of NO2 over London, over Paris, over Brussels and Milan, which were quite heavily hit, and at the same time are also highly polluted cities. Moving on, and then late March, India started taking aggressive steps. And you can, if we go back a year, in year 2019, and look at the period of say 25th March to April 2019, you can see NO2 concentrations over Indian cities. You can see really high concentration over Delhi, Mumbai, and other major cities across, and also Northeast India. Well, if you look at 2020, the pollution levels over these metro areas suddenly dropped because of the shutdowns, because of the government's aggressive policies. There was around 40 to 50% drop in NO2 over Mumbai and Delhi. Okay, but you can still see really high pollution levels in the atmosphere in Northeast India, especially due to power plants. So these were the stress locations that still are producing a lot of NO2. However, if you look at particulate matter, this is a fine concentrations of particulate matter, 2.5, and you can see the percentage decrease along major Indian cities. For example, Delhi, Pune, and Ahmedabad, these are big towns. The decrease was more than 50%. It's a tremendous decrease. But at the same time, other cities also showed a considerable amount of decrease. These graphs are kind of biased, I would say, because some cities have dense network of observations, and that's why you see large percentage decrease or more robustness in the data. But PM signals, therefore the PM signals are strong, but it doesn't mean that other cities, the PM didn't decrease that much. You can think of an analogy for PM similar to the testing that we are having for coronavirus. The more testing you have, the more dense network you have for PM. Similarly, the sample size, the bigger the sample size you have, you will have more better understanding of the disease. Going back to United States, in the US, NO2 concentrations are generally low because of tough environmental regulations. And US declared a national emergency mid-March after World Meteorological Organization declared it a pandemic. And you can see the NO2 levels during the month of March compared to the decadal mean. So the levels are quite low, as you can see in this animation over the left side. And the cities across the Midwest and Northeast US, you can see the reductions happening considerably well. When you move towards the eastern side, You can see cities like San Francisco, Los Angeles, the concentrations of NO2 again started decreasing. And there are two primary reasons for the reductions in NO2. First is due to COVID-19 reduced emissions that we can imagine because of the shutdowns, and second is the differences in weather. And it's important to isolate both these factors, and it requires more rigorous assessments. NOAA did some kind of assessment where they looked at the weekdays and weekends pollution for the March 2020, and NO2 pollution reductions during the weekends was considerably more because of the reduced traffic. PM concentrations in the United States, if you look at it, they show the similar trend. And PM is important, similar to NO2, because of many hazardous solid and liquid waste particles suspended in the air. And it leads to premature deaths in people with heart and lung disease. And Larry will gonna talk more about PM particularly later in the talk. So now the important question is, what is the relationship between COVID-19, temperature, and humidity? So here I show 3 cities across the US, which are under different climate zones: Chicago, New York, and Louisiana. And you can see the y-axis is different. On the x-axis, I'm showing January, February, March, April, and May, 5 months of this year. And if you look at the deaths, Chicago has reached around 4,000 deaths, New York 30,000, around 30,000 deaths, Louisiana around 2,000-3,000 deaths. When we look at the temperature is everywhere for all these 3 different cities. And the dots here represents the deaths here. So when we look at temperature and humidity, we don't clearly see any relationship between the number of deaths and how COVID-19 is impacting all these different cities. So in conclusion, the relationship between temperature, humidity, and COVID-19 transmission is inconclusive. And that is a very important question, because as we're moving from spring to summer, we don't know how climate, especially temperature and humidity, are going to play an important role in either transmission or of the virus. And as we are going blind, kind of, as we will move towards fall, when there will be a more flu season, we would not be able to isolate the COVID-19 impacts, and then in December. So we need a lot of research investments trying to answer these questions. Now going to the questions related to the populations, how they're reacting to shutdowns, we are looking at the mobility data, and this is the mobility data for India. So you can see after the Indian government started the shutdowns on 21st March, the mobility suddenly decreased a lot in a lot of sectors, except for residential mobility. People were still going within their neighborhoods and walking and spending their time, and that was reasonable. So we see populations reacting seriously to COVID-19 issues. While in US also, and specifically Chicago, there was a similar trend. You can see mid-March, the mobility suddenly decreased with respect to driving, walking, or transit. But late April and mid-May, you can see the mobility increasing. And the reason for that is, especially populations started going to parks, public parks. There's a 54% increase compared to baseline for people going to parks. But residential mobility was kind of stable at around 10%. Whereas other factors were kind of in decline. Retail and recreation was in decline, transit stations, and workforce. So that brings us to the question of, because a lot of populations lives in urban environments, and these are the people who are getting impacted with COVID-19. So our urban environments are multi-scale, interdependent, social, and natural engineered complex systems. And here I present a schematic of these urban environments. And you can see we face a lot of challenges in urban environments. For example, high energy stress, high urban heating, poor air quality, lack of green spaces, less open spaces for recreation, and physical activity. Plus, now we had COVID-19. Okay, this is something new with which all of us are trying to figure it out. What we really want are resilient urban environments with adaptive choices. We need low energy stress, improved air quality, more green spaces, and more space for recreation and physical activity. In this resiliency schematic that I have drawn, now we have to add higher readiness for public health challenges like COVID-19. So this is important as we try to understand COVID-19, its relationship with public health, with air quality, and with societal living. So my utopia of urban environments being more robust and resilient had one more layer of uncertainty that we need to work on. So if we think in totality, we have many answers, but many questions remain too. And these relate to these following points. First, dramatic emission reductions happened in 2010, and they are likely caused by shutdowns, as we know, or stay-at-home orders, or differences in weather. And we need to isolate them quickly and learn. It's not a hard task, but it takes time and resources. Secondly, the relationship between temperature, humidity, COVID-19 transmission is inconclusive. So we need to work on those aspects too. Third, climate change due to deforestation and human-wildlife conflict. There are very strong interplays between these two topics, and we need to make more investments and collaborative work with epidemiologists and climate community so that we can understand the relationships of how and what it impacts. So overall, teasing apart climate with other factors is a challenge. And it's us to dive deeper and understand those challenges. For all these things, we believe that we need more focused research investments if we want to understand all these things. So in this regard, we at the University of Illinois are working towards a health vulnerability toolkit, where we are taking social vulnerability, okay, and climate, COVID-19, and from our colleagues, there's a vaccine mapper at University of Notre Dame. So if we can involve a lot of interdisciplinary aspects, it becomes an open opportunity as well as a challenge to design coordinated reconnaissance efforts for global health vulnerability toolkit. And this is, I'm just showing for the US, but our goal is we want to design for the whole world so that we can understand these relationships between meteorology, air quality, public health, and social vulnerability to not just COVID-19, but maybe future other diseases or other related health impacts. So we started working on US, and this is the overlay map of COVID-19 with social vulnerability, and you can see some relationships. And the relationship, something looks like this. So this is the cluster mapping, and you can see a cluster mapping of social vulnerability versus COVID. And the red areas are, which are highly vulnerable as well have high COVID-19 cases. So, and this kind of also, these are preliminary results, and we are investigating more and looking at the air quality and bringing in air quality in the picture and seeing how does it interplay. So overall, the takeaways are, there's a positive urban environment, there's a positive environmental changes happening. For example, reduced air pollution, cleaner water, which I didn't talk about, reduced traffic, reduced noise. It's good for health, right? Because of COVID-19. These are unintended consequences that we are having due to COVID-19. But the big question is, do we need crisis for change? Okay, can the humanity work towards this change without a crisis? We all work for the crisis, we are working as one world, one society. Do we need crisis for change? Can we sustain this improved climate or environment? Can we prepare for climate change as a pandemic? So these are the questions we are trying to answer, and we are hoping others will join us in these efforts. But at the same time, there are many challenges ahead of us. We need to understand human behavior issues, reduced physical activity, increase in poor mental health that's going on right now. And also the new 6 feet distance society. How will it impact work and public spaces, transportation, etc.? There are many more questions that we need to think about. Okay, with that, I'll end my talk and introduce our last speaker, Larry. And Larry is a Blue Waters professor at the Department of Atmospheric Sciences at School of Earth, Society and Environment, and also at National Center for Supercomputing Applications. Larry will further discuss the role of aerosol pollutions on health and climate, discussing why reduced aerosol pollution also reduces the death rate from COVID-19, and discuss an upcoming NASA satellite mission for better understanding the links between aerosol pollution and human health.
Okay, so I'm going to pick up from where Ashish left off. Okay, so picking up with the emissions, we have to keep in mind that emissions don't necessarily equal concentrations, although they are related. What we have here are emissions taking place off the surface those pollutants end up in the atmosphere where they undergo chemical transformations. And then they are heavily impacted by the weather. There's convection that takes place that transports the pollutants vertically. The wind, there's horizontal winds that transports it long distances. There's interaction with clouds, and precipitations can scavenge those pollutants, all of which help control the ultimate concentrations that we breathe. So given the emissions, right, scientists try to work out not only what the changes in emissions that we have, and trying to characterize what those emissions are. That in itself is a challenge. But given those emissions, we try to model the entire process here to determine and predict the concentrations that we end up breathing in. These predictions, of course, help us assess our scientific understanding of the processes. They go on to inform policymakers, and they provide warnings to the public. They require models. Scientists make use of very sophisticated models, and this is very generic, whether we're talking about weather, climate, health, society. It's a foundation of all sciences that we build models to make predictions, and these models have inputs. Now, when we're talking about COVID-19 impact, we are basically looking at how it impacts our inventories of emission. Okay, so as we just heard, we expect a reduction in emissions in numerous sectors. And one of the things we have to deal with are the uncertainties. There's uncertainties on how these emissions have changed. There's uncertainties in the models, and these end up propagating to produce uncertainties in the predictions. When these uncertainties are very large, it may demonstrate that we have a poor scientific understanding of the processes. Large uncertainties makes it very difficult for policymakers to make policies, and large uncertainties leads to warnings that the public may not take as credible because the uncertainties are so large, we'd end up being in error quite a bit when we produce a prediction. So in order to help improve our predictions by reducing uncertainties in the models and in the inputs, we have to have controlled lab experiments. And in nature, this is very, very difficult to do. So for example, if you take a hurricane, and we're trying to understand how, understand how the hurricane is going to behave, it is difficult to do these things in the lab. So observations are key, modeling is key, validating our predictions is key, and looking at this in large scale events, such as tornadoes, hurricanes, volcanic eruptions, long-term CO2 increases, and now COVID-19. These large-scale impact events are excellent ways to test and improve upon our scientific understanding and reduce uncertainties for future predictions. Now, we heard a lot about NO2 and CO2 from Ashish and Don. I'm going to focus now on aerosols. Aerosols, a lot of which you're familiar with. They include ash, pollen, sea salt, soots. There's a lot more, but these are the more familiar ones to you. These are just particles that are floating in the air. So when you hear me say aerosols, I'm talking about particles that are floating around in the air. Sometimes these put on fantastic displays as observed from space. So in this particular case, we're looking at a region that's more than 1,000 kilometers long. And we're looking at Saharan dust blowing off here of Africa over the Atlantic. And these stretch thousands of kilometers. And just to point out, you know, the dust that we see over here is in fact several days old. It takes time to travel 1,000 kilometers. There's also familiar man-made sources of pollutants, such as from industry, from car use, from agricultural burning, to burning of biofuels for cooking and home heating. And these too can also have fantastic displays as seen from space. Here I'm showing the effects of agricultural burning over Borneo, and just to give you a sense of scale, this is a few hundred kilometers across. And in fact, I was back in September, I was in the Philippines studying the effects of smoke transport on the air quality in the Philippines. And I spent a few weeks there, and you can read more about it on my website. Now, these pollutants not only span hundreds of kilometers, as I just showed you, they can expand over thousands of kilometers, as we see here in pollution over India, or more than up here in the Ganges Valley and out over here as well. This is where more than half of India's population resides. And when you look at these high pollution events at the surface, you know, I just want to point out when we see it looking this way, as in this picture on a polluted day, these are the aerosols that are causing the scattering. It's not the gaseous pollution that's reducing the visibility. Now, these aerosols go ahead and we breathe them in, of course, and our body is designed in part to filter some of the larger particles out before it gets into our lungs. But the smaller aerosol particles, those having diameters that are less than 2.5 micrometers, so this is about, I don't know, about 100th the size of a human hair. These are referred to as PM 2.5, and these smaller particles are able to make it all the way down into the deepest parts of our lungs, and these go on to cause pulmonary and cardiovascular diseases, amongst other things. In fact, the World Health Organization estimates that 91% of the world's population is breathing PM 2.5 at concentrations that are considered to be polluted air. And that this goes on to kill about 7 million people every year prematurely. Now, a lot of epidemiological studies have focused on aerosol size. So here we're looking at aerosols smaller than 2.5 microns in diameter. But of course, we expect chemical composition of the aerosols to be an important factor. But I want to point out that those studies really haven't been done for chemical composition, and the studies so far have been pretty limited. They're limited by the small number of people that are in these studies, limited to only a few countries like the US and Europe, where we have just a few monitoring sites to do these kinds of studies. There's also the issue of the availability of medical records that are, you know, these things just are not easily had. So in order to deal with this issue of limited surface monitoring sites, we've gone ahead and tried to make use of our current satellite technologies. So here's a annual average outdoor PM 2.5 concentration derived from the Terra satellite. You could see right away that a large source of PM 2.5 actually comes from dust. But keep in mind that while yes, dust is an important source, many other regions of the world, this is in large part due to human activities. So yes, this was derived from the Terra satellite, which was launched in 1999. I'm on the Terra team, and I was there since the beginning. And I can tell you that we have not designed Terra to go after PM 2.5. This is really an effort to make do with what we have up in space, and that maps such as these carry quite a bit of uncertainty to it, which propagates into our understanding of the impacts of aerosols on human health. I'd like to point out that with Terra or other satellites, we have an inability to get at the chemical compositions. So this is still a problem that we have. And there's still the issue of limited cooperation and organization around sharing medical records to do large-scale epidemiological studies between aerosols and human health. So to get around all that and solve these problems, we put together an international group shown here. This is a NASA-funded mission called the Multi-Angle Imager for Aerosols. We launch in just a couple of years, May 2022, and it involves cooperation amongst many agencies from NASA to the CDC, to National Institute of Health, and it includes many universities such as Illinois, Harvard, as well as international partners in India, the Netherlands, Canada. So Maya measurements here will be combined with chemical transport models and pollution health records to better understand the connections between aerosol pollutants and health problems such as adverse birth outcomes, cardiovascular and respiratory diseases, and premature death. This is just to show you that Maya will be targeting a number of cities. We have our primary target areas, list shown here in blue. We have international agreements in place for sharing health records with our collaborators. And the study is expected to take 3 years to complete. I'd also like to point out that Maya, while we are targeting cities, we can't target all cities. We do have a list of secondary target areas where we do have collaboration with investigators for sharing health records. The issue at hand is that Maya is a cost cap mission. We have a fixed price in terms of dealing with the hardware, the management of the data, the science analysis afterwards. There's actually, in terms of instrument capability and in fact our scientific capability and computational capability, we could easily handle adding more targets to Maya, but we are a cost cap mission, and the only way we're going to be able to expand our study to other regions of the world is to find new sources of funding. So what does all this have to do with COVID-19? Well, these higher concentrations, as studies have shown, that higher concentrations of PM2.5 do lead to higher cardiovascular and respiratory diseases. These diseases happen to be pre-existing conditions that increase the risk of death from COVID-19. And in fact, the studies are now coming out. This one's in peer review right now. From a group from Harvard, and what they've concluded using US data, that a small increase in long-term exposure due to PM2.5 leads to a large increase in the COVID-19 death rate. And they've gone ahead and quantified that here, showing that a 1 microgram per meter cube increase in PM2.5, this is long-term exposure that I'm discussing, is associated with an 8% increase in the COVID-19 death rate, which is quite shocking. So the basic message here is that by cleaning up the air, this will make us a healthier population, which would in turn reduce the death rates associated with COVID-19. Now, what do these particles, these aerosol particles, also have to do with climate change, since this is also what we're talking here? Not only do these aerosols, as you saw in those satellite image, scatter sunlight back out to space, it turns out that water vapor condenses onto the aerosols to form clouds. If there's no aerosols in the air, there wouldn't be any clouds. So it's not surprising that a change in aerosols leads to a change in clouds, and you change the clouds, you change the albedo of the Earth, that is the amount of sunlight that's scattered back out to space. You change its greenhouse ability. You change the precipitation efficiency, since the precipitation efficiency depends on the drop size distribution of the clouds, which in turn depends on the aerosol size distribution and type. And you end up changing the life cycle or longevity of the clouds. So we expect then, we fully expect then that clean clouds have very different characteristics than polluted clouds, and to some extent this has already been shown with observations. Why is this important? Well, clouds cover a large part of the Earth, about 70% at any one time. They're the largest modulator of the radiation budget, and they are a key component of the hydrological cycle. So given the important role that clouds have on our climate system, it's not surprised that this process that I'm discussing, that how a change in aerosol impacts the change in clouds, which impacts the change in Earth's climate. This process is actually our leading source of uncertainty in anthropogenic climate change predictions. And there's a lot more work to be done in order to reduce those uncertainties. And again, just like long-term increases in CO2 has tested our ability to predict future climate changes. Same thing here is that these changes associated with emissions from COVID-19 is one of these large impact events that we will be studying on how not only did it impact how COVID-19 has changed the emissions, how it changed the concentrations of pollutants we breathe in, but also on how it changes cloud microphysical properties. Again, I want to stress the importance of weather in all of this. In looking at data and trying to tease out the measurements of concentration, how much is that is due to a change in emissions, how much is that due to a change in weather. This is tough work. We've already seen some of this from Ashish, and we've seen this a lot in the news media, in fact, where you find analyses comparing this month to last month, or comparing this month to the same month last year. We need to keep in mind there is a seasonal cycle, there is year-to-year variability, and there's even long-term changes that are taking place. For example, over China, over the past 10 years, there's actually been a significant reduction in the overall amount of aerosols in the air. So they are working towards cleaning up their air. There's still quite a bit of work to do, of course. So just an example of what I mean by all this, here is actually a time series of the aerosol optical depth over all of India. You could consider aerosol optical depth here as an optical measure of the aerosol concentration. We're going from, this time series spans 20 years from the beginning of the Terra mission to the beginning of this year. And what you could see in this measurement of aerosols, that there's quite a bit of seasonality that takes place. So over India, we see the highest concentrations in aerosols taking place in June, with the smallest concentrations taking place in December, and you have the strong seasonal signal that takes place. There's also quite a bit of variability from year to year, right? You can see that there are outliers, such as this one here in 2002 in June. Another outlier here in 2011 in June for high concentrations, and the same is true for outliers in minimum concentrations. So in order to characterize, trying to tease out COVID-19 effects, one also has to deal with this variability, and it's important to have very good records like we have from Terra to help characterize what the seasonality and that variability is. This way we could better tease out the COVID-19 signal from the weather noise, if you will. Now, these studies should not only be focused on the country at hand, for example, as in the time series I'm looking here. We also need to look at non-local large-scale effects, because there are teleconnections around the world associated with that impacts the weather in any one region. The most popular one, of course, that makes it into media is El Nino. We always hear about this year was a strong El Nino year, or a weak El Nino year, strong La Nina year. So the weather, the large-scale events that are taking place, for example, with El Nino in the Pacific Ocean, does have an impact on the weather around the world. So when we're looking at these kinds of time series here, and we're looking at outliers, we also need to look at whether we had a strong El Nino year, for example. So these can't be just local studies, they have to be global studies as well. So there's a number of challenges. I'm not going to go through that here in doing these kinds of scientific studies and dealing with massive amounts of data from satellite. These satellite volumes are in this petascale range. Rather than go through these challenges, I want to just make clear that these challenges that we often talk about, whether these are big data challenges or scientific challenges, in a lot of ways, we actually know how to solve these problems. The main issue has to do with people and resources, and that we don't have enough people working on these problems, and the amount of resources to tackle these problems is limited. So we're always trying to focus our resources to do the best we can, given the limited amount of resources that we have, and limited amount of people that we have. So to recap the three talks, basically, I want to say that, reiterate what Don was saying, human activities have made a large measurable impact on climate. This is projected to increase. There is in fact no scientific debate on this anymore. I've yet to go to a conference in 25 years and hear someone argue against this. And some of these conferences are attended by tens of thousands of scientists. COVID-19 is a high impact event that will allow us to further test our scientific understanding in a range of disciplines, not just earth sciences, but medical sciences, earth sciences, and so on, social sciences, and so on. This will ultimately lead to reduced uncertainties in our predictions and our improved scientific understanding of all these processes. I also want to point out that changes in air quality is not just driven by reduced emissions caused by COVID-19, but you got to deal with the seasonal and year-to-year variations in the weather, which itself is impacted by large-scale weather events in other parts of the world. There are, of course, many great reasons, both environmental and health, for cleaning up the air. The lessening the impact of COVID-19 and other future pandemics on death rates is just one more great reason for cleaning up the air. Of course, these investigations are extraordinarily challenging and require focused research investments for true advancements. And finally, Maya and the health vulnerability mapping that Ashish was talking, these are very cool things. They're lots of fun to work with, and they're really needed. And so we hope that we could get more people involved in these activities to help out. And with that, I'll say thank you. I'll turn it back to Erin.
Yes, thank you. I'll start with reading a couple of the questions. We got several questions about what happens as countries open back up and life returns to a more normal pattern. Reports show that air pollution in China is rebounding as they begin to recover, reaching levels higher than those at the same time last year. Do you anticipate a similar staggered rebound across the world? And how can we ensure that NO2 emissions don't increase much after lockdown is over?
I'll try to take this. So I think that's a true statement that we might see, and we will likely see a rebound happening in air pollution, not just NO2, but particulate matter and other things. But the question is, what can we learn from what has happened or is happening right now in a live experiment? People will start going to work, industries will open, there will be a lot more anthropogenic sources. But it's for individuals, it's for communities, it's for government, national and international organizations to make policies so that we don't have to face COVID-19 like situation related to climate, which might be even more difficult to manage than COVID-19. So we need to take a step back and make really strict policies of what we can do, what we cannot do, what we should do, what we should not do, so that we don't have a rebound as high as it was earlier. Of course, there'll be a rebound, but what can we do? Yeah.
I think we can also say that this is not the time for the US EPA to be reducing its controls on air and water quality that are going to affect us over the coming years.
Mm-hmm.
That's right. Tightening those restrictions is just going to lead to poor air quality in the across the U.S. and elsewhere, and it's just not good for anybody.
Okay, so here's a second question. How might the EPA loosening restrictions of environmental policy during COVID-19 impact environmental conditions, similar to what you just mentioned?
My guess is it won't have that much of an effect near term, because companies don't like to just be pushed around one way or another very quickly, because they know the next administration could rapidly change things in a different direction. So my guess is this won't make a big difference, but I think in some individual cases, we will see a significant increase in emissions just because a given company or sector thinks they can get away with it.
Thank you. A couple of participants asked if you could talk about what role can high school and college students play in climate change? How can students contribute positively to improve the climate situation?
Oh, the students can have a huge impact, if nothing else, by getting their parents to be thinking about this more. There's so many different ways. You know, you can have a huge impact on the legislature and our leaders by letting them know that you think this is one of the most important issues, which it is, and that it's really going to greatly affect your lives, because you're going to have to live with the consequences of what we do over the next 10 to 20 years. So you know, I think if you focus in on those things in particular, as well as trying to get others to you know, reduce their own emissions, all of us need to learn how to be more efficient in our use of energy. But I think the biggest impact will be how we affect those who represent us.
Let me add to this that there, for students, there's particular in the K through 12 range, there's a number of great programs that are out there for educating students and for getting students actually involved in research. And if you do a Google search along this line, you'll find it. Let me call out one example. It's the NASA Globe program. So if you type in, if you search for NASA Globe, it'll come up. And it's one way, and there are many such outreach programs, so this is just one of them. And it's one way for students to get involved with their teachers at school. So students, let your teachers know about these programs, and ask that they develop modules and lab exercises, and data collection. That's the cool thing about this. Some of these programs, it shows you how to do crowdsourcing, if you will, of data. And now that data gets fed back to some NASA scientist who's doing an analysis of the data that you've collected as a student. So yeah, there are these types of activities as well that can be done to help promote climate research and contribute to climate research.
I think one additional point is...
Thanks for sharing that. I think that sounds like an exciting way for students to get involved.
I think one additional way to increase this awareness is for people to talk more about climate change. As Catherine Hoey says, the more you talk, the more you will learn and educate people. So I think that would be critical.
And I think we'll do one more for the sake of time. And this was a popular one. Are you aware of any economic researchers connecting research models to the aerosol pollution and computed healthcare costs associated with that air pollution?
This is certainly being done and has been done. In fact, the very first, one of the first papers, I think it's one of the most cited papers in all of science, actually, is from an economist, Pope. If I recall, he's from the University of Utah. And he was the first to show the link between PM 2.5 concentrations, or was it PM 10? I don't quite recall. It's a fairly old study now. But yeah, it's the first that connects PM 2.5 concentrations to adverse health outcomes. And yeah, that was an economist who did that.
Yeah, there's actually been lots of studies that have been looking at those relationships.
Mm-hmm.
Great. Thank you. And feel free to reach back out to us if you have additional questions or would like to engage otherwise. But thank you very much for joining us and have a great day. Stay well.